Hi, good morning. My name is Samuel Adebayo. I'm from Queen's University, Belfast, in the United Kingdom. Today I'm going to outline a theoretical framework for automating assembly of intermeshed steel connections using off-the-shelf robotics. And our work is in collaboration with Kingston University in the United Kingdom, University of Texas, San Antonio, and New York University, and others. So, prefabricated beams and columns are usually the main components of steel buildings. And this usually, especially when it involves on-site assembly, involves mainly 4 steps, categorized into the following. The lifting of the members, whether from the welding shop or from wherever, or the manufactured area, to then transporting of the members to the construction site, and then aligning the members so that you can then bolt them and connect all of the bolts and all of the weldings together. However, this usually involves very risky situation and is quite unsafe. So aside being unsafe, the typical steel connection require a number of bolts, which are usually not very suitable for robotic assembly. And the welding is usually very difficult for on-site assembly, and for this reason it reduces reusability and involves increased inspection and requirements so that there is high precision cuts there. And the difficulty to control the quality is also a very big challenge. However, there is a new type of connection that has emerged with less bolting requirements. It's a novel steel connection, and this is known as the Intermeshed Steel Connection, also known as, in short, ISC, as you can see here. On account of all the aforementioned, we identify the following research gaps and then our contributions. Previous robotic systems either required custom mega robots or sort of a dedicated support structure. Neither is deployable on a typical site. So our work closes 2 gaps. Number 1, the workflow. So we conceptualize a 3-stage human-robot workflow for intermeshed steel connection using a standard KUKA robot. And then we develop a dummy construction site with small-scale column-to-column intermeshed steel connection for future demonstrations. Our proposed strategy involves 3 main stages: the pre-assembly stage, the assembly stage, and the post-assembly stage. The pre-assembly stage involves the member lifting and the member transportation, and the assembly stage involves rough alignments, the fine alignments, and the connection plate attachments, while the post-assembly stage involves the bolting. In any case, both the pre-assembly stage and post-assembly stage involves the human operator, while the assembly stage involves only the robot. During the assembly stage, the 2 columns are brought together at a lateral distance of between 10 to 20 centimeters, while the orientation at this very point is not considered. And during the fine alignment stage, the robot is then going to place the 2 column plates together such that the distance between them is approximately 0 centimeter. At this very point, the orientation is very important. And finally, the connection plates is placed between the 2 together, the 2 columns, such that at the later stage, the humans are going to then bolt the connection plates to the column-to-column connections. Zooming in on our proposed strategy, the dotted arrows show the flow of data from the building information modeling to perception, and even to the control and the communications as well. And if you notice, we've got a fail-safe loop here to check for avoidable and obstacles. And if the safety module flags, say for example, an obstacle, we pause for a manual override rather than forcing a path. Although our work is a proposed strategy, a theoretical framework, so to speak, we decided to come up with a small-scale assembly scene. As mentioned earlier, we used a column-to-column connection of intermeshed steel connection for assembly process. And then we selected a column dimension from the repertoire. We have selected the 305 by 305 by 97 and then we scaled it to 1/3, which is essentially around 103 by 100 mm. And then in our scene, we've got the robotic system. As you can see here in our schematic diagram, we have camera C1 to C3 feeding the post estimation and the object detection, all strategically placed in different areas, in the area views, the frontal and the side views. And then we've got also, in addition to the cameras, we've got the depth camera to give us depth details of object in the scene from the perspective of the robot. Here is our actual small scale assembly scene. We've got these two ISC members. We call this the ISC bottom, and then we've got the column and then the connection plate. All of these are referred to as the ISC members, so to speak. When we call our work automated steel assembly, it still involves a combination of manual and robotic process that sort of avoid any additional structural system and follow the typical assembly steps. And you may ask, why did we still have to keep the crane operator and manual bolting? We did that for two reasons. Number one is for pragmatism, and then number two is for incremental adoption. Pragmatism because 10-ton members exceed manipulator or any sort of robotic manipulator payloads, so that cranes that already exist on site can essentially do the heavy lifting for us. And incremental adoption because letting crew members bolt or do the bolting, maintain familiarity and cuts across and cut through all the change management and all the frictions. In all, our proposed strategy involves 4 software components and modules: the perception, the control, the safety and communication systems. All of these map cleanly onto the existing site workflows, so there is no overhauling the whole system or changing a big change in the whole existing system. In conclusion, this novel robotic assembly process of intermeshed steel connection will increase safety and efficiency, and the small-scale assembly setup will demonstrate the feasibility of the assembly workflow. But it is not without its limitation. One limitation is the synchronization between the manual and robotic process. We're still working through that. And only small-scale assembly process for column to column has been considered. So we're still looking at widening and looking at other assembly processes that needs to be considered. And bolting operation require design, and manufacturing of special end effector and computer vision algorithm is still a bit of a challenge. We're currently working on that as well. And our future work would involve the doing research on the automation of the bolting process, whether to come up with an automated process to do this, which will further reduce human involvement in the whole process. And we're looking at designing of human machine interface for the assembly process and looking at field trials for large-scale intermeshed steel connection. We are grateful and acknowledge the financial support of the National Science Foundation under the award 2222815 by Science Foundation Ireland, Award 21 US 3797, and by the Department for the Economy, United Kingdom, through the grant USI 218. And we thank our participating universities: the New York University, USA, University of Texas at San Antonio, USA, University College Dublin, Republic of Ireland, and University of Galway, Republic of Ireland, and finally Queen's University, Belfast, Northern Ireland, United Kingdom. Thank you very much. I'm happy to discuss and answer any question. Thank you.